All right, I'm going to be going over coin change. This is Leetcode 322. You're given an integer array coins representing coins of different denominations and an integer amount representing a total amount of money. You need to return the fewest number of coins that you need to make up that amount. If that amount of money cannot be made up of any combination of coins, return -1, and you may assume you have an infinite number of each coin. So the test case I am going to display is the second one here. um, where we have 1, 2, and 5 with an amount 11 that we're starting with, and our output ends up being 3. Um, and as you can see, the explanation here, we use 5, 1 as our denominations. And so I drew up this in a scale draw, and inside of this, we have part of our tree that we're going to use to really see how this works. So if we start with 11 here, and we we go down this branch and use 5, we are left with 6. We use 2, we're left with 9. If we use 1, we're left with 10. And this will be the whole trick here, is to start with a total and then subtract, and then continue to find what you're left with, and then continue to subtract. And obviously this has a nice recursive structure. And so if we go down this branch, we're left with 6, and again, we'll go down this branch again, and we're left with 1. And then it's very easy to just go down. If we try to go down 5 again, we obviously get to -4, and that's no good. We want to basically go down the 1 branch, which leaves us at 0, and those are 3 steps. Third step. So this is kind of the brute force way of doing it. We could just recursively try all the options. And this is obviously vastly inefficient. And how can we avoid some of this pre-computed, or how can we avoid duplicating some of these calculations? And the answer is, well, before we go into the answer, let's show exactly what we're talking about. So if we go down, say, the 1 branch here, we end up at 10. And then say we go down the 2 branch, we end up with 8. And say here we go 2 and 1, and we end up at 8 again. These two are both at this level of the tree. They're both at the same level of the tree right here. And once we get the denominations or the steps to, like, the minimum number of steps to get to 0 from this spot, we will also already know the minimum number of steps to get from this spot over here. So we can use, once we reach this point, if we've already calculated this down to whatever the number of steps is, we can then use that number of steps here. And this can vastly reduce the number of computations that we have to make. So with that, let's get into kind of the code. And I love to use just a depth first search helper function here. So let's use a depth first search here. And we're going to start off with our total. This will be an int, and then we'll have, which will also be an int. This will return a int, and we're going to union this with a float, which I will explain later. So what we're going to do is we're going to first basically come up with, I just want to get to this test case. Yeah. So we're basically going to try to, if the total equals 0, we know we can return 0. If the total is less than 0, we need to return infinity. And how we denote that in Python would be float infinity. And we want to return infinity here because we're trying to find the minimum number of steps. Next, what we're going to do is we can try to take and not take. And these are a common pattern with these types of dynamic programming questions. We can run DFS, total minus coins of I, because we're taking our total amount, so the total amount, and we're subtracting it by whatever we're taking. We're subtracting it by whatever coins that we're using right now. And then we would keep I the same here because we can continue to use the same denomination an infinite amount of times. And then we'll have not take right here, and we'll call DFS on this. And this will be just the total. And this time we will increment I. And what we can do is we can return the min of these two. Now this should be the normal way to do everything. So we've got the total, which starts off as the amount. We also have which equals 0 to start off. Now, we have to remember the case where everything's infinite and we cannot come up with an answer, and there we return -1. So we can say if does not equal does not equal float inf else -1. And we can recall this because, well, I'll get into the hint for why we can recall this. But first, I'm going to run this without the optimization, and then we'll get into the optimization. And we made an error here. The last thing we need to check is or if I is out of bounds. So if I is equal to the length of coins, we need to that. This might time out, and hope it does, because what we can then do is we can add our optimization. So the trick here is to know that each branch, if we ever have the same total, we know we can calculate that just once and we can continue to use that over and over again. So we'll have just a little memo up here. This will be a dictionary. And inside this memo, it will be the total and the we'll have a tuple here of the total. So an int, and that will be our key. Our value will be the steps. So our value will be here. And the one thing I forgot to add would be right here, we need to increment this every time we take, because that's an extra step. But we don't do it here. So there's a good catch. And what we can do is we can ask if the tuple of total in memo, we can just return the memo. Uh, and then we need to remember to assign it here and then return it. OI in memo. And there we go. There is the answer. Let's submit this. And it worked. Cool. Thank you so much.